So let us look a little bit in details the unbalance and the harmonics, as we said earlier. Okay, so we said it is balanced when the magnitude of all the phases at all the time they are equal. Are we getting it? It becomes unbalanced when they are not equal. Okay, as you can see on this diagram to the right. So we see that some of the phases, they are higher, okay, in magnitude. This is 100% the power unit. So if it is 415, what we have here is 415. If it is 220, what we have here is 220. Okay, so you see the fluctuation, some are less than that 220. So the voltage is unbalanced. Okay, so we'll see the reason why we need to protect our electric motor system against unbalance when they occur. So if you have equipment or instrument that you can use to look at the power quality in your system, so you have this kind of display on such equipment, okay, that is power quality analyzers or meters. Okay, so this is the one to the right is the phasor diagram, and to the left we have the information of what we have on the system. Okay, so you see the voltage levels. We have 236.4, we have another 234.5, and we have another 239.3. okay, so if you also look to the right, you will see the phasor diagram, and you see the phase angle. You see that they are not entirely in phase, and this is what is shown on the left of so the first one, if it is 0, you see that the second one is not 120, because we are having 118, and this third one is not 240, we are having 233. Okay, so you see that the phase difference is a little bit abnormal. It's not normal or as expected. Are we getting it? So let us look at how we can calculate the unbalance from this system. The unbalance, usually what we do is that we take the average, okay, of these three voltages, okay, and subtract each of them from that average value. Then we'll now use the highest deviation, okay, take the highest deviation and divide it by that our average. So what we have will become the unbalance that we have in the system. What we mean is that we'll add this to this and this, and if we do that, we have 200, and if we add this to this and this, we have that is 236.4 plus 234.5 plus 239.3. okay, when we add, we'll have and divide by 3, we'll have 236.7. 236.7, that becomes our average voltage. So this average voltage, when we take the difference between 236.4, we have 0.3. Then difference with that is the average minus 234.5, we have 2.2. okay, then the average, which is 236.7 minus 239.3, we have 2.6. okay, so the highest is that's 2.6. Are we getting it? So the highest is that 2.6. That is the highest deviation. So we'll now take that 2.6 and divide by the 236.7, which is the average, and we'll have 0.011 which is about 1.1%. Okay, so the unbalance in this case is not much of an issue. Are we getting it? So unbalance between 0.5 to about 2.5%, they are a kind of acceptable. It depends on the tolerance that your establishment set or they agree on. Okay, so the unbalance that is more than 2 in some establishments, anything that is above 2 is unacceptable. You have to do everything possible to bring it back to that, down to below, far below 2. Are we getting it? Okay, so that is for the unbalance. And the unbalance, why it is very dangerous, can be shown in this diagram that you can see. Okay, this graph. So on this graph, you see the percentage of unbalance and the expected temperature rise. So usually an unbalance of 1 percent can create current unbalance of about between 6 to 10%. You can imagine that. So that will mean that the heat that will be lost, the dissipated heat or energy that will be lost from the system in the form of heat, okay, will increase by that amount, 6% and 10%. Are we getting it? So if that happens, we know that clearly that heating effect will affect the reliability of the electric motor itself, and thus the system. So if you look at it, 1% voltage unbalance can result to about 2% temperature rise of the system. Then 2% voltage unbalance, 8% rise of the temperature of the motor system. Then 3% unbalance, you can see, are we getting it? You can see if say we have temperature rise from the ABNs during normal operations, okay, say about 40 degrees Celsius. That is what we have. You can see that 2% voltage unbalance can cause a temperature rise of about 4 degrees Celsius. Just imagine that we have higher unbalance in the system. What will happen? You will see that the temperature will increase, and that will affect the insulation integrity and subsequently cause failure in the insulation and cause a shorting of the turns and burnout of the windings. Are we getting it? So it is something that we must guide against in the electric motor system. So harmonics, you know, we said ideally what we expect to come into our system is sinusoidal, but in reality we do not have that. Okay, so what we have in reality is this kind of distorted waveform. Why is it distorted? It's because we have other voltage signals, okay, that are superimposed onto this fundamental signal that we expect to go into our system. So that is what you are seeing on the right. If this is the fundamental, these are harmonics, okay, 2 times the fundamental frequency, 3 times the fundamental frequency. So all of this superimposed onto this will now give us this distorted waveform. Okay, so this distorted waveform, remember the only usable one here is this. So all of this will go into our system to create problems. All these energies, they must be dissipated somehow, and they will be dissipated within the system. Okay, so we must guide against it. Okay, so we can see the effect, the distortion, that is the black waveform, which is what is so all of this superimposed into this fundamental waveform cause all of this distortion. So this is the kind of waveform that we will be seeing mostly in our system. Okay, so let us look at the effect of voltage variation on the motors. Okay, so if you look at the graph, you see that we have percentage variation as against percentage changes in the motor performance. So we are looking at a few performance parameters. Okay, the full load current, power factor, efficiency, starting current, and torque. Are we getting it? So you see, if there is no unbalance, you see that the motor will be operating at its equilibrium, maximum efficiency. Look at the efficiency curve. It is operating at the maximum efficiency. Are we getting it? Which means that the efficiency at this point is at the highest. Look to the left, you see drop in efficiency. Look to the right, you see drop in efficiency. Why are we experiencing all of this drop? Let us look. If we have under voltage, okay, of 5, 10, or 15%, how does it affect? You see the full load current increases as the under voltage is increasing, okay, and drops as we are experiencing no voltage variations, no voltage unbalance. Are we getting it? So as the voltage unbalance is increasing to the positive, you see too the full load current is also increasing. And once the full load current increases, that will increase the heat loss in the winding and reduce the efficiency. Okay, that is one of the reasons why we have reduced efficiency on the left and on the right of the equilibrium point.